Hello, my name is Mark Leclerc, and I'm NoviFlow's VP of Strategy and Marketing. Welcome to this series of videos that NoviFlow is producing to showcase how fully programmable OpenFlow switches, such as NoviFlow's Novi switches, can help make today's networks more responsive, more efficient, more scalable, and less costly. NoviFlow believes that SDN can not only integrate seamlessly with existing and brownfield networks, but that it can also add significant new capabilities to these networks. This video series is intended to demonstrate how NoviFlow implements SDN to do networking differently and better via practical real-world examples. NoviFlow's NoviWare implements a packet forwarding pipeline that uses network processors instead of general-purpose x86 processors to run its code. Another key OpenFlow capability leveraged by NoviFlow in our products is the experimenter feature. In order to enable both easy customization of OpenFlow solutions and to foster innovation, OpenFlow includes a mechanism that allows hardware and software developers to define new functions based on their own priorities and those of their customers. This is called the experimenter feature. Now, there's nothing experimental about the experimenter feature. These are production-grade extensions to the OpenFlow specification, which NoviFlow supports and will continue to support in our products as they evolve. If these functions are deemed useful by the wider SDN community, they can subsequently be adopted into the OpenFlow standard, which NoviFlow will also support in our products. It's in this spirit that NoviFlow has created a series of our own OpenFlow experimenter features that take full advantage of the programmability of network processors. These features have been adopted by many of our customers and implemented widely, including in large-scale commercial networks. To show in a practical way how these features can make networks more responsive, more efficient, more scalable, and less costly, in this video, we will show examples of how to do packet payload matching and handling, layer 2 encapsulation/decapsulation, and using tunneling protocols in completely new ways. We will show actual running code examples that can be downloaded and reutilized. We hope these examples will give the viewers ideas on how they can also leverage the full richness of SDN and NoviFlow's Novi switches to solve networking problems differently. Also, please note that all the code showed here will be available on our website, www.noviflow.com, as well as via the Inside OpenFlow website. For these demos, I'd like to introduce Davide Trentin, NoviFlow's team leader of system testing. Davide, if you will, please.
In this first demo, we'll show how UDP payload matching can be used to inspect what's after the L4 layer. More precisely, we will try to match on the msearch and T5 word of SSTP packets by using our UDP experimental extension. To do this, we implemented a way to configure the table to specify which size and which offset we want to match on inside the UDP payload. And then only after having configured the table, we can add the flows to use it. In this setup, I'm using a RIO controller running on this machine. We extended the OFCTL REST API already provided with RIO to use our own extensions. And this machine is being used to generate the traffic and see how matching is being executed and action are being applied to the traffic. So I'm using here the Postman REST API to send the various commands. The RIO controller is running here, waiting for the commands, and these Wireshark are capturing the traffic from and to this machine. The first thing I need to do is to configure the table, specifying what size and what offset I want to match on. In this case, 8 bytes for the size to match the msearch word, and the offset is 0 because this word is placed at the beginning of the UDP payload. I first send this message, and then I need to configure the match field that I want to use in the table. In this case, I am specifying the UDP payload among the match fields. So right now in the switch, here I have a connection to the switch. The table is configured to support UDP payload matching with 8 byte size and 0 byte offset. I then need to specify the flow entries to match on these words. This first flow entry I'm matching on the msearch word inside the payload. These hexadecimal values are the ASCII values for the msearch characters. So all packets with the msearch word inside the payload will be modified, pushing a new VLAN with the VLAN ID of 50. And then a second flow is being pushed to match on the notify word. Since this word is shorter than msearch, I am masking the last 2 bytes to ignore them. And I'm pushing a VLAN of 60 in this case. So right now in this switch, I have these 2 flows, and I'm going to send some traffic to match on them. So first, I will send the packet including the msearch word. So this packet has msearch at the beginning of its payload. It's being matched and transmitted at the output with a VLAN of 50. If we look at the flow entries again, we'll see that it's the first flow only which matched and pushed the VLAN 50. If then I send the second message with the notify word inside, we see that this has been matched as well. The notify word is here at the beginning of the packet. We can see how these bytes are the same that I am matching on here. And this packet is being transmitted at the output with a VLAN of 60. In the second demo, we show another similar feature of Novi switches. It's matching on IP payload. We'll also show how we can set IP payload and UDP payload fields. Like in the previous example, we'll configure the table to specify on which size and offset we want to match inside the IP payload, and then add flows to use this match field. For this example, we use the VxLAN packets. So VxLAN is after IP. We can match on what's inside the VxLAN tunnel actually, using this experimental match field. So the first thing I'll do is configure the size and offset. In this case, it's 6 and 16 bytes. And then I'll specify what match fields I want to support in the table. So in this case, I want the IP payload and the tunnel ID as well, because I'll be matching on the VxLAN VNI as well. Once the table is configured, I can add one flow. In this case, I'm matching on an IPv4 Ethernet type, a tunnel ID of 10, which would be the VxLAN VNI, and an IP payload 0, 1, 2, 3, 4, and 5, which would be the MAC destination inside of the packet inside the tunnel. On this packet, I will change the value of the VxLAN VNI using the experimental extension set UDP payload and set IP payload. So the resulting VNI would be a combination of what I reset with IP payload, which is AB, and what I set with UDP payload, which is 3 and 4, 1, 2, 3, and 4. So in the switch right now, we have the table configured like this. So supporting matching on IP payload and tunnel ID. And for IP payload, size of 6 bytes, it's a MAC address, and offset 16 to go matching inside the Ethernet destination inside the VxLAN VNI. And the flows have only one flow matching a specific tunnel ID of 10, a specific MAC address, and then setting a new VxLAN VNI. When I send traffic, if I send packets not matching, for example, a first packet here, which has a wrong VNI, it's not matched, and the second packet, which has the wrong address inside of the tunnel, the wrong Ethernet destination inside the tunnel, they both didn't match. You can see in the statistics of the table that both packets has been processed, but none match the flow in the table. When I send a packet matching. So this third packet, it has a VxLAN VNI of 10, like specified in the flow, and a inner Ethernet destination 012345, like specified in our experimental match field. So this packet matched the flow entry, and it's been transmitted with a different VNI, which is composed by these two values that has been set using our experimental extension, AB1234. Like in the previous demos, we'll be showing another extension that allows to match on the payload of data plane packets. In this case, it's the MPLS payload. So this allows us to match the inner packet inside an MPLS tunnel. More specifically, we'll be using this feature to match on the IP source of the packets inside the MPLS table. To do this, like in the previous examples, we need to configure the table to match on the right offset and the size that we need. In this case, it's 4 bytes for an IPv4 address and an offset of 12 to match on the inner IPv4 source. We'll then configure the table to support the MPLS payload matching. And finally, we will add one flow entry to match on a specific value for this IPv4 address, which is 10.0.1.1. Only packets matching with this inner IPv4 source will be modified, removing the MPLS tag before transmitting at the output. So if we look in the switch, the table is configured to match an MPS payload with a size of 4 and offset of 12. The flow is defined like this. This is the value we'll be matching on, and these are the actions that we will apply. When I send traffic, if I send packets not matching this flow, for example, this packet has an inner address of 10.0.0.1, so it didn't match. The second one is 10.0.1.0, so it didn't match. The statistic of the table confirmed that there has been no match with this flow entry. But if I send the packet with the right address, this packet has the desired inner IPv4 source after the MPLS tag. So it's been matched, and the packet transmitted has no more an MPLS tag attached to it. In this demo, we'll show a different feature of NoviFlow switches, which is the ability of encapsulate and decapsulate other types of tunnels which are not part of the standard OpenFlow specification. In this case, we were talking about L2 MPLS. NoviFlow switches allow two new actions, push and pop tunnel, which can allow the creation of L2 MPLS tunnels and the decapsulation of encapsulated packets. To use these features, we'll need to configure the table to support the desired match field. And for this example, I'll be adding one entry, which will be matching on a VLAN ID of 10. And on packets with this VLAN ID, it will push an L2 MPLS tunnel. And in the action, I can specify the values of the outer Ethernet addresses and the tunnel labels. I will also add a second flow entry, which will identify packets which are already encapsulated in L2 MPLS and with specific MPLS tunnel and VC tunnel labels. And on these packets, I will apply a pop tunnel action which will decapsulate them. By looking at the flows in the table, we can find these two flows that I just defined. I will show how it behaves the encapsulation first. So this packet comes with the VLAN ID of 10, so it's matching the first of the two flows that I added. And on this packet, it's then pushing an L2 MPLS tag with a new Ethernet layer, the MPLS, the tunnel label, PC label, and inside we find the original packets. The values of the newly pushed layers are those that are defined in the action itself. So addresses and labels are defined in the flow entry. If now I send another packet which is already encapsulated, this packet is matching the second flow entry, the one with the pop tunnel action. So this flow is having the tunnel label of 100, BC label of 200, like defined in here. And at the output, we can see that the transmitted packets doesn't have the L2 MPLS tunnel anymore. And we are only transmitting what was inside the tunnel. In this demo, we show a combination of the features we showed in previous demos, so matching on IP and UDP payloads, and as well of the encapsulation of a GTP tunnel in this case. In this case, we will send GTP traffic. We'll use UDP and IP payload matching to match on the inner IPv4 destination and TCP port destination. Only packets matching specific values of these fields will be decapsulated before being transmitted at the output. To achieve this, I am configuring the table 0 to match on IP and UDP payload. And also I am configuring the UDP payload to match on a size of 2 and offset of 30. This corresponds to the inner TCP destination port. And then I will also configure the IP payload to match on a size of 4 and an offset of 32, which correspond to the inner packet IPv4 destination. Once the table is configured, I can add this flow entry. I'm specifying an Ethernet type IP protocol which allow me to recognize only GTP packets, and an IP payload of 10002, which needs to be the inner IPv4 destination to identify the packets to be decapsulated, and the UDP payload of 80, which is the desired TCP destination port. Only matching packets will be decapsulated and then transmitted at the output. In the switch, you can see the installed flow entry, and I will start showing how it behaves with packets which are not matching this flow entry. For example, this first packet, it has a GTP tunnel and an inner destination IP of 10003, which does not match the desired 10002, so it's not matching. And a second packet which has the right IP destination, but the wrong TCP destination port, 81 instead of 80. So both packets, they didn't match the flow entry. And I will now send another packet which has the right IP4 address and TCP port. So this packet, it has an inner IP of 10002 and an inner destination port of 80. It matched the flow entry. You can see in the flow entry packet count incremented, and it's been transmitted at the output without the GTP tunnel. What's left at the output is only what was inside the GTP tunnel.
We hope this video has provided you some clear examples of the usefulness of SDN and how NoviFlow has extended OpenFlow's already rich feature set to take advantage of the advanced programmability of network processors. I'd like to remind you that all the code examples we show in this video are available on NoviFlow's website at www.noviflow.com. We also encourage you to visit InsideOpenFlow.com, a site dedicated to the rapid adoption and deployment of OpenFlow. It provides everything you need to get started with OpenFlow: code, development tools, link to educational materials, and realistic test network infrastructure. All open source under the MIT license. If you have any questions or want to talk about how NoviFlow and our products can help you leverage the full goodness of SDN, please contact us at contact@noviflow.com. Thank you for viewing this video.